Hello everybody and welcome back to another video. My name is Codenatics, and in today's video we're going to be checking out this really cool 2017 US Open Contest Bronze Division problem called Modern Art. So the link is in the description down below, or you can just hard code it into the URL if you wanted to. But take some time and read the problem by yourself, brainstorm some ideas, and when you think you know it or when you need some help, just come back and we'll go over it together. Okay, so essentially, this problem is all about a 2D grid. We've got the grid has dimensions n by n, and what Picasso has done is the cow in question here is Picasso has painted these rectangles all along the board, and Picasso has painted them in sequence. So Picasso would paint one and then another and then another, so they might overlap. And so the question is, of all the possible colors we see on the board, which are the ones which you could have painted first? So let's take a look. Here is the sample input in question right over here. If you want, you can take some time and confirm they're the same. And so we want to know, of the possible colors here, which ones could Picasso have painted first? Alright, so first off, 0 is not a color, so we're just going to ignore that. So we have three possible colors here. We've got color of 2, a color of 3, and a color of 7. These are our three possible colors. Let's do that a bit better. There we go. So 2, 3, and 7. Now we want to know which ones of these could have been first. But how do we know that? Well, let's take a look. Can 3 be first? Well, we know that Picasso is only going to paint one rectangle per color. And moreover, when she paints using that color, she doesn't use it again. So if we take a look at the 7 right here, we see that the 7 would have obviously had to been a rectangle like this. And once Picasso painted that 7, Picasso would have had to paint something like this. So what this tells us is that since this 3 right here overlaps the second 7 box, we know that 3 obviously could not have been first. So we can do something like this. This gives us an idea here that we can go over every single pair of visible colors and see, is there an overlap between those colors? Because if there is an overlap, we can immediately eliminate one of the colors. But how do we tell if there's an overlap? Well, in order to tell if there's an overlap, we need to know the boxes that Picasso painted. So we need to be able to figure out a way to say that, oh, this 2 was this 3 by 3 box, and this 7 was this 2 by 3 box, and this 3 was this 1 by 2. Or do we? Note that we are only given the final state of the canvas, so we have to consider all possible ways that Picasso could have gotten to that final state of the canvas. Now this is really just a fancy way of saying we want to take the minimum rectangles, because that's going to allow us to get the maximum number of possible starting colors. If that doesn't make sense, mull over it a bit, and it should make a bit of sense once you actually think about it, because obviously the smaller the rectangle, the less chance there is for it to overlap, which means the more possibility that another color is also going to possibly be a first. Okay, so if we want to take the smallest rectangle, for 2, that would be this. Now how did I come up with this? Well, do you see any 2 outside of this box? Because I don't. So obviously it would have to be the smallest possible. But you might be saying, well, hold up, what about this? Well, note that this 2 is right there, and that's outside of the box, so that doesn't work. Or what about this? Well, that excludes this 2. So if you went over trial and error and looked at all possible ways that you could come up with these bounding boxes, you would see that, yeah, this is the bounding box that encompasses 2. But how do we figure that out? Well, what we can do is notice that there's no 2 outside of this box. Moreover, let's consider this box right here. Why is this not a bounding box? Why is this not the box that encompasses all 2's and the smallest one possible? Well, that's because none of these guys, none of you let me use a better color here. Let's see. None of you. That is not a better color. None of you guys right here are 2. None of them are 2. So we know that we can shift in that bounding box, that right-hand bounding box, by 1. Aha! That gives me an idea. What if we took a look at the 2 which had the highest position? So for example, we took a look at, let me change the color right here. We took a look at a 2 which had the highest position, a 2 which had the leftmost position, the 2 which had the lowest position, right? And then the 2 which had the rightmost position. Something like this. So what I mean is, there's no 2 above this 2. And there's no 2 to the left of this 2. There's no 2 to the below of this 2. There's no 2 to the right of this 2. Well, then we know that the box is just this. Because there's no other 2's and there's 2's all around, obviously that has to be the box. So what we can do is we can go over all of the 2's and see what's the maximum height, the minimum height of all of the 2's, and then what's the leftmost coordinate, I guess, and the rightmost coordinate. And those are the dimensions of our bounding box. Boom. We got a way to figure out the bounding box. Let's test it out. This 2 has got, here we go. This 2 has got a position of 0, 0. So I'm going to keep track. Left, that is not how you spell an E. Left, right, up, and down. Sorry, my laptop is lagging. Alright, there we go. Left, right, up, down. So left, we got a 0. Right, we got a 0. Up, we got a 0. And down, we got a 0. Because those are all zeros. And then if we take a look at this 2, well, we got a 1, 0. So we're going to change this right coordinate to 1. Because, well, now we have a new rightmost coordinate. As for up, it's the same, and down is the same. Now if we take a look at this 2, we'll notice that we've got a position of 0, 1. So the left is going to stay the same, but the down, now the down is going to change. The down is going to become 1. And before I write this 1 so that I don't have to keep erasing, when we consider this one, the down is going to be 2. And so this gives us left of 0, right of 1, and remember this is encompassing, so the left is going to be the left and the right is going to be the right, and then an up of 0, and then a down of 2, 0, 1, 2. Boom. So what's in between? This is the region that's in between, and now we found our bounding box. So that's just a proof that it works. And once we find our bounding boxes, it's not that hard to check. We just have to check the intersection of these bounding boxes, or rather, more simply put, we just have to check, does any 7 intrude on this 2's bounding box, which yes it does. We can cross off 7. Sorry, that was a bit fast, so I'll reiterate that. If any 7, or whatever number, intrudes upon 2's bounding box, we can't use. Since 7 intrudes upon 2's bounding box, we can't use 7. Because there's a 7 there, and there should have been a 2 there, so that means 7 had to be painted after 2, which means it's not possible for us to use it anymore. And then similarly, if we take a look at, let me cross this out, if we take a look at this 3, well, when we consider the bounding box of 7, there's a 3 here, so we can cross out the 3. And there's nothing else, there's no other bounding boxes. Well, obviously there's the 3's bounding box, but nothing intrudes on that, so we've got nothing to do, and that leaves us with just 2 remaining. And take a look at 2 right here. There's only 2 remaining, so we see what do they want. They want the output of a count of the numbers that could have been drawn first. Well, there's only 1 that I see here, so the answer is 1. Amazing. So we've got exactly what we wanted. And I think this algorithm, it definitely works. It's not the most clear. And it's not entirely, you might not be convinced that it does entirely work. So pause the video now and convince yourself that it does work, because we're about to go coding. Okay, so let's pull up Visual Studio Code here, and let me pull up this C++ file. So we're going to hashtag include bit slash std c++.h and using namespace std, and we're going to throw up our int main. Alright, so for those of you who don't know what bit slash std c++.h is, it's really useful because it automatically imports everything that you want. It's a very nifty command. Okay, so we've got that. Now we're going to have two files. We're going to have art.in and art.out. So here we go. Let's pull up the in file. And we're going to copy and paste our input right there. And the out file can just remain. And I don't care about this. Okay. So now the first thing we've got to do is we've got to read in our input file and output file. So I'm going to say, let's see here, FRE open, and then art.in for reading. And then the file is going to be stdin. So we can read it using standard input. And we're going to copy this, and we're going to use out instead of that. And we're going to make this a write. Boom. Now I've got that. Let's move on to actually taking in our input. First things first, we're going to need to take in a single number, 4. So we're going to say int n. Let me space this out properly. Int n, sin n. This is going to take in our input of 4. We are going to create an array. So we're going to create a vector of vector, because that's going to basically represent our two-dimensional array. And we're going to make it a vector of ints, v, array of size vector, or array of v of size n, and then another vector of int of size n. So what this does is this initializes, okay, we've got n for our first dimension, and then that each one of those is filled with a vector of size n. Boom. Okay, so we've got all of that filled up. It's time to read that in. So for int I is equal to 0, I is less than n, I plus plus, and then for int j is equal to 0, j is less than n, j plus plus. Now we're going to read in all of our input. But here's where we can be clever. What we can do is we can create a vector of bool, and since we only get up to 0 to 9 as their colors, we can say vector of bool pos, or actually let's call this ants array of size 10. So what is this? What is this array I've created here? What I've created here is an array which represents, for every single integer from 0 to 9, is it possible for that integer, which is technically a color, to be our first starting color? And so that's what it is. But currently it's initialized with everything for false. So what we're going to do is we're going to read in v of I of j. And we're going to say if v of I of j is greater than 0, because remember, 0 is not a color, then we're going to say ants of v of I of j is equal to true. So we're going to start off by saying that any color we see, as long as it's there, it's possible for it to be the first. Now what we've got to do is go over and eliminate the colors that we don't think is possible, or rather eliminate the colors that we know is not possible. So remember, we've got that we're going to eliminate 3 in this case and 7, and we'll be left with 2. So let's take a look at that. So here's what we're going to do. We're going to go over every single color that we still see. So for yeah, so here's actually the tricky part. We need to go over every color, but we also, we need to go over every single color that's on the board, but we also need to eliminate colors if we know they don't work. So I'm going to just create a second one called exists. And I'm going to say ands of v of I of j equals exists of v of I of j is equal to true. Okay, there we go. So now for int I is equal to 0, I is less than 10, I plus plus, if exists of I, which means if it exists, we've got to find its bounding boxes. So we're going to keep track of it. Int L is equal to 0, R is equal to, well, rather let's do it this way. We're going to say int L is equal to N, R is equal to 0, U is equal to 0, or so then we'll start with D is equal to N, U is equal to 0. Okay, so what have I done here? I've essentially initialized left to be N, right to be 0, D to be N, and U to be 0. Why have I chosen these values? Well, remember, we want to minimize the value of the left, which means we want to start it out as large as possible. And we want to maximize the value of right, so we want to start it off as small as possible. And the same for the rest of these. So now we're going to say for int j is equal to 0, j is less than 10, or j is less than n, j plus plus. For int k is equal to 0, k is less than n, k plus plus. If v of j of k is equal to I, L is equal to min of Lj, R is equal to max of Rj, U is equal to, or D is equal to min of dk. Let's see, is that an actual, that's not an actual error. U is equal to max of uk. There we go. So now we've got, using just this amount of code, we've figured out our bounding box. How cool is that? But let's actually implement the second part of our solution, which is we've got to say for, we're just not going to initialize things here. Or actually we can. We'll say for int I is, or for int j is equal to L, j is less than or equal to R, j plus plus. For int k is equal to D, D is less, or k is less than or equal to U, k plus plus. So now we're iterating over everything in our bounding box. We can say, we've got to initialize this as int. We can say if v of j of k is not equal to I, then ans of v of j of k is equal to false. There we go. So that's our algorithm, and now we just have to output everything. So we're going to say for int I is equal to 0, I is less than 10, I plus plus. If ans of I, we'll need to keep track of a count, so we're going to say int count is equal to 0. If ans of I, count plus plus. And then we're going to output count. There we go. Okay, let's do a quick runtime analysis here. We've got an O of n squared. We've got an O of n squared cubed. So this entire thing is going to take O of n cubed because we've got an n squared right here, another n squared right here, so this entire thing is O of n squared, but then we wrap it with another for loop, so that's going to be O of n cubed, and then we've got another O of n. But n, if we take a look at our problem statement right here, we see that n is basically at most 10. So O of n cubed is going to be O of 1000, which is perfect. That will pass, no problem. But before we submit, let's make sure that our solution works. So let's pull it up here. We're going to say g++ minus std equals c++ 11 minus wll minus o2 ma.cpp minus o ma. And so what this is going to do is this is going to compile in C++ 11 our code, and it's going to put the binary into a file called ma. So now I'm going to run this file. It's going to output a value of 0. And that's why you always check. Let's figure out where we went wrong here. So let's debug. We're going to say for auto I in exists, sout I with a space, and then sout/n. And I'm going to do the same for ans. So we're going to run it now. And let's take a look at our output. We got it filled with zeros. That's not exactly what we wanted. We wanted it filled with ones. So we check if v of I of j is greater than 0. Let's instead of being risky like that, let's do it like this. Equals true. Okay. And we'll recompile it and run it again. Art.out. See, that's not good. Let's output v of I of j. Art.in. Okay, there we go. So that should output our array. Whoo-wee. That is not good. Ah, I see the issue here. Okay, I made a mistake. When we're reading the input, alright, so this is all a problem with reading our input. We're gonna read in a string s, sin s, because we need to get each character, and we're gonna say v of I of j is equal to s of j minus 0. Okay, that's the entire issue we've got. So first let me make sure this works, and then I'll tell you guys why it works. Brilliant. Okay, so the reason why we were getting an error is because in our input over here, you notice that we don't actually have our values space separated. They're all consecutive, which means when I use sin, it's looking for a space or a /n. And the place where it finds a /n is right here. It's this new line character. And VS Code is really helpful, and it shows us, you see that little, it's highlighting something there. What it's highlighting is a /n character. So it's looking for that, and it sees that, so it's going to think all of these are 1. When actually, I want it just to be this is 1, and this is 1, and this is 1, and this is 1. So the way that I work around that is I read it in as a string. Now reading it in as a string gives me this entire thing. And better yet, I can access each individual element. So I do that over here with accessing s of j. But then I do this minus 0 in single quotation marks, which is the 0 character. And the reason I do that is because that allows me to extract it as an int. And obviously, you could try and do convert it to a string, or do something like convert the character itself to an integer instead of like just getting its ord. But just subtracting the 0 character just makes the most sense. Oops. And so what that does is it says here. Let's take a look. I have 0 here, and if I subtract 0 from it, what do you think we're gonna get? Obviously, we're gonna get 0. If I have 1 here and I subtract 0 from it, you might be confused. How do we do this? Well, the little-known secret, or well, the well-known secret, is that characters are all actually integers. And this 1 character is the integer right after 0. I don't remember their exact ords, but that's how it is. So this is actually going to be 1. And you can guess that 2 minus 0 is equal to 2. And so on and so forth. That's exactly what we're doing. And so then the rest of this works the way it's intended. We just weren't reading the input correctly. So let's move on to submitting our solution. And to do that, we're going to have to go back to our... There we go. Okay, so I have plugged in the file right here, ma.cpp, and we're going to set it to C++17. Now you might be saying, well, you compiled it in C++11, why are you going to submit it in C++17? The reason I submit in C++17 is because 17 is actually faster. The higher the C++ level you have, generally, the faster. So let's submit this. And now it's going to wait for an available grading server, and we're going to submit. And it takes its own time. And there you go. All correct. Okay, so let's just recap. What did we do? We went over by first taking in our input right here. That's this big chunk of code right here. Then we computed our bounding boxes. We went over every single possible color. We checked if the color existed, because remember, that was a clause. And we found the bounding box using this bit of code right here. By getting the leftmost, rightmost, downmost, and upmost, I don't think those are words, but just roll with me here. We got all of those coordinates, and we know that those are the bounding boxes. And then we checked, is there any other color in those bounding boxes? Because if it is, we know that that color would have to be painted over this color, which means that color could not have been first. And finally, we went over any color which could still possibly be first, and we added that to a counter and outputted that counter. So that's the entirety of modern art from the 2017 US Open Contest Bronze Division. If you guys did enjoy, please don't forget to like and subscribe. It really means a lot to me. And leave a comment down in the comment section below letting me know what you guys want. I promise I do look at those and they are useful to me. And with that, I'll catch you guys in another video.